During an earthquake, friction-generated heat is produced along discrete fault surfaces. Evidence of past temperature rise and thus an earthquake is difficult to identify in the rock record. However, fault-slip paleothermometers have been developed that link textures or geochemistry to coseismic temperatures. Figure 1 shows some paleotemperature proxies and their temperature sensitivities. Our SCEC-supported research compares two of these proxies, thermal maturation of organic matter or biomarkers, shown with the green box, and low-temperature thermochronometry, shown in the blue and red boxes. We are applying these dual approaches in the Punchbowl Fault and leveraging prior work by my co-authors that demonstrates past coseismic temperature rise. This allows us to compare the kinetics of these systems and hopefully more accurately characterize coseismic temperatures. Biomarkers are naturally occurring organic material found in rocks. They alter as a function of temperature, and one index that measures this alteration is the MPI-4 index. A higher MPI-4 value is evidence of higher temperatures. Figure 2 summarizes biomarker data from the Punchbowl Fault and shows MPI-4 indices for different components or domains in the fault. Savage and Polisar documented evidence for temperature rise at the principal slip zone, or PSZ, compared to other domains only centimeters away. Low-temperature thermochronometries such as the zircon, uranium, thorium, helium, and apatite fission track systems are typically used to track slow-cooling processes such as mountain building, but are also sensitive to high-temperature, short-duration events such as those caused by earthquakes. Figure 3 shows the temperature and time required to reset the zircon, helium, and apatite fission track systems. The lines show the temperature at which 90% helium loss for the zircon-helium system and 100% of fission tracks annealing in the AFT system will occur. The slope of these lines mean that these thermochronometers can be reset over a range of temperatures, but there is a direct trade-off between the magnitude and duration of temperatures required to reset these systems. Importantly, the temperature sensitivity of a zircon grain varies as a function of its accumulated radiation damage from uranium and thorium decay or metamictization. The crystal lattice of a grain is damaged if the grain contains a higher concentration of uranium and thus appears darker in plain polarized light. This damage can cause increased helium diffusivity. Thus, we can target grains with a range of metamictization and temperature sensitivities even in a single sample. The Punchbowl Fault is an ancient strand of the San Andreas Fault and is located 3 kilometers away in the Devil's Punchbowl region. It juxtaposes Miocene Punchbowl Formation with Precambrian basement. We chose to investigate the use of thermochronometers as fault-slip paleothermometers here because my co-authors found evidence of heat along the slip surface using biomarkers. Additionally, the Punchbowl Fault is an archetypal example of strain localization and the development of a thin fault zone. To date, we have reoccupied one of the same locations as my co-authors, our sites EA20-1 and 2, and a new site 4. These figures show images of sampling sites in the different domains of the fault zone. These domains are easily distinguished by color and discretely collected at the centimeter scale with a pocket knife and hammer, similar to the biomarker study. The units include highly comminuted PSZ, ultracataclysite from both sides of the fault, crystalline basement, and Punchbowl Formation. After mineral separation processes, I am excited to share that there are whole zircon grains amenable to uranium, thorium, helium analysis, and apatite fragments amenable to apatite fission track analysis. Datable grains are found even in the most comminuted materials. Importantly, the zircon grains demonstrate a range of metamictization, allowing me to target high-damage metamict grains that are more amenable to resetting and reconstruct a more complete thermal history of these rocks using the full range of metamictization. If data show that the PSZ experienced heat similar to the findings of my co-authors in the biomarker study, this shows that damage in zircon persists through high temperatures. We anticipate that the thermochronometry results will show evidence of an increased temperature rise closer to the PSZ and decrease in temperature rise centimeters away, consistent with existing biomarker data. These results will be manifested as an increased helium loss in zircon and shortened track lengths in apatite. In summary, we hope thermochronometry data patterns will show coseismic heat along the discrete slip surface, which we can compare to biomarker results and better quantify coseismic temperature rise along the fault.